In this video, I'm going to continue talking about vector-valued functions and discuss things that we can do with them. So, for instance, we could find the domain of a vector-valued function, and this would be just like finding the domain for a regular function, except for that you have to look at all three components. Look at all three, or two if it's two-dimensional components. So we could do the domain. We could take a limit of a vector-valued function. We could take the derivative of a vector-valued function. We could take the integral, find the integral of a vector-valued function. And all of these are performed the exact same way, where you would take the limit, derivative, or integral of each separate component. So you do this component-wise. Okay, so some other facts. If r of t is position, so if the vector-valued function is describing the position of some particle or of something, then if you take the derivative of it, and this should be pretty intuitive, the derivative is going to equal the velocity vector. Also, that derivative, I'm going to change color here because this is one that's easy to forget. That derivative is the parallel vector for the tangent line. I'm going to star it on both sides too. That's really easy to forget. So we can find the parametric equations of the tangent line, because now we can find a parallel vector from a derivative of a vector-valued function. So that's something else we can do with it. We could take a second derivative of position and find the acceleration vector. And we could also find the speed. Maybe I should put that over here. If we find the magnitude of the velocity vector, the magnitude of the velocity vector would give us the speed of the particle at that point. Okay, let's do some examples. So let's do a domain question first. So let's find the domain. So we're going to find the domain of the vectored valued function. Notice I'm going to use s instead of t, just to get you used to some different variables, of e to the negative 2s in the times natural log of s in the x component, 1 over s minus 1 in the y component, and square root of s plus 1 in the z component. We're going to look at each different one of these three components all separately, figure out the domain separately, and then bring them all back together into one kind of larger domain. The domain is going to be all of the values of s where this will work. And by this, I mean all three of those functions, where all three of those functions will work. All right, so let's look at them all separately. If we look at e to the negative 2s, that does not have any holes in it. E to the 2s is continuous everywhere. And so there's nothing to consider there for the domain, because the domain is everything. Now natural log, recall that natural log looks like that. And remember that, so the x values, the domain value are those, the domain values are those s's. And so the only s's that we could plug in then would be ones where they're greater than 0. X does not quite reach 0 on this graph, and it's never negative. So the only values of x that work for natural log of x are ones that are bigger than 0, x's that are bigger than 0. All right, so that's the first part of it. 1 over s minus 1. This one has a division by 0. Everything else is okay, but s can't be 1 because we can't divide by 0. And for square roots, the only thing we can input into a square root is a positive number or 0. So s plus 1 would have to be greater than or equal to 0, and this means that s would have to be greater than or equal to negative 1. Now to bring this all together, I'd like to use just a simple number line. And it looks like I've got some considerations here at 0, at negative 1, and at 1. There's some stuff going on. Okay, so for this first one, I'm going to mark on this graph that s can be greater than 0. So I'm going to put a hole at 0, and then mark that it could be anything greater than 0. Moving on to the next line down, s can't equal 1, so I'm going to put a hole right there. So there's a hole at 0, a hole at 1. And then the third one, s is greater than negative 1, so, or equal to. So that one, I could fill in the dot on that one, and then it's everything greater than negative 1. Now, the domain is the s's that we can put in that will work for everything. So we want to look at where all of these things overlap. So we have overlapping here and from there on. So we have overlapping in between 0 and 1. So in between, but not including 0 and 1. And then we have overlapping from 1 to infinity. There's the domain. It includes all the s's. I'm writing down all of the s's where there are no division by zeros, no negatives and square roots, and no negatives or zeros in natural log. All right, let's do another example. This time, let's do a limit example. So let's calculate the limit of the vector valued function t, sine of t over t, and 4t squared plus 3 all over t cubed plus t. And let's do the limit as t goes to 0. Now we're going to look at this component by component. So for the first one's easy. Plug in 0, we get 0. It's all good. We get a number. Now the second one, if we plug in 0, we get, so I'm going to make some notes here kind of at the bottom. Maybe I'll do it in a different color just to say I'm looking at this guy right there. All right, so if we plug in 0, we get 0 over 0. Now 0 over 0 means that we can apply L'Hopital's rule to this. So L'Hopital's rule, we could take the derivative of the top. The derivative of the top is cosine. Let's see. Yep, it's a cosine. And the derivative of the bottom, the derivative of t, is just 1. And then we could retake the limit. The limit as t goes to 0. If we plug in 0 into cosine, the cosine of 0 is 1. 1 over 1 would be 1. Okay, so that limit, sine of t over t, that limit is 1. The limit on this next one, now when I've got polynomials, I look at the values of t and I ask myself which one is bigger. In this case here, the bottom is bigger So the bottom is going to control. And as the bottom goes to 0, if the bottom is getting smaller, the whole thing is getting big. All right, so that would be the limit for that guy. And just so that you can kind of remember this, if these match, so if these were both t squareds, they do the same thing then. Nobody's winning, nobody's getting bigger. And so you can pull the numbers out in front. So that limit would have been 4 over 1, it would have been 4. If the top had been, say, a 4 and been bigger, then it would control, it would kind of win. And then we would go to then the top would be controlling and it would go to 0. Okay, so I have my limit. We could either say this, or really we could say that this limit does not exist. I'd really accept both answers because of that infinity in there. Some books kind of want you to specify that if it goes to infinity, it doesn't exist. And some want you to just specify that that limit's going to infinity. And I'm happy with either, as long as you can get that value of infinity. Okay, do another example. Let's say that we have the curve where r of t is equal to t and then t squared plus 1. Now, if we sketch this curve, I don't know how to sketch parametric equations. I have to put it into x's and y's. I know that x is equal to t, that's the x component. I know that y is equal to t squared plus 1 because that's the y component. And if t is equal to x, I can plug that into y and get that y is x squared plus 1. Parabola. Oh, plus 1. Let's erase that parabola and shift that parabola up 1. Okay, that's better. So x, y, the parabola is shifted up 1. All right, so now let's find, and then we'll sketch it. I just want you to get a bit of a visualization here for it. Let's find the velocity vector. So the velocity vector, pretty easy to find it. Just take the derivative. So derivative of t is 1. We're just doing this component-wise. Derivative of the y component. Derivative of t squared is 2t, and derivative of 1 is 0. Okay, so there's my velocity. This is the velocity vector here, this 1 and then 2t. And let's sketch it when t is equal to, let's go with 2. So when t is equal to 2, I can plug that in here. And I get the vector 1, 4. Now the vector 1, 4, I could draw that from anywhere. I could draw that from the origin, but it wouldn't really mean anything in this picture. If we find the position when t is equal to 2, so the position when t is equal to 2, I've got to take that t equals 2, I've got to plug it back up into the position here, so that would give me the vector 2, and then 2 squared is 4, plus 1 is 5. That vector 2, 5 is going to point to the point 2, 5 on this graph. I wanted to get that position because now this vector 1, 4, if I go from the point 2, 5, so if I start there and I go over 1 in the x and then up 4, kind of running out of room here, but the vector is going to look just like that. And the reason that I wanted to draw this for you is that I want you to notice that that vector is tangent. That vector, the velocity vector, is tangent to the curve. That's all I wanted to get across on sketching that. So finding the velocity vector, pretty easy. You just take the derivative. If we wanted to find, say, speed at t equals 2, then we just need to find the magnitude of that vector 1, 4. Magnitude of a vector is the square root of all its components squared. 1 squared plus 4 squared. So the speed would be square root of, what's that, 16, 17. That's how fast it's going. So here's my velocity vector. Okay. We could also find the acceleration vector. The acceleration vector, we just need to take one more derivative. So I need to go back up here and find r prime with the t's in it. There it is. Let's take a derivative of that guy to find the acceleration vector. This will be at any time. And that vector will be 0. Derivative of 1 is 0. Derivative of 2t is 2. And there's my acceleration vector. And let's do one more example. Let's find the position. If we know the acceleration, if we know that the acceleration is t squared plus t sine of t in the x component, 2 and 0. And we're going to need the initial velocity. The initial velocity, let's go with 0, 1, 2. And the initial position is the origin. Okay, so we're now going backwards. Given acceleration, we need to take an integral to get back to velocity, and then we'll have to do another integral to get back to position. So we need to, first of all, in order to find velocity, we are going to have to integrate that acceleration vector. T sine of t to 0. All right, so integrating this. When we integrate the first time, let's see, t squared, integrate that, t cubed over 3. In order to integrate t sine of t, I need to do either integration by parts. I like to use tabular, so with tabular, I'd go t1, 0, those are derivatives. Sine of t, I take integrals of these, so integral of sine is negative cosine, the integral of cosine is sine, and then we keep that sign, keep that negative sign. Multiplied diagonally, the first term is multiplied by a positive number, the second one's multiplied by a negative. So for that next integral, we get negative t, the negative's coming from in front of the cosine of t. A negative times a negative is a plus, sine of t. And we need to add a constant. So I'm going to call that C1. All right, next component. So now I'm looking at that 2. If I integrate 2, the integral of 2 is 2t, and then I need another constant. And I'm running out of room here. And then let's see if I can erase this integral. I can't yet. Okay. The integral of 0, well, that's just going to be some constant. So that would be a C3. Sorry, I kind of ran out of room there. All right, now what we need to do is use the initial velocity and find those constants. So initial velocity is the velocity at 0. So I'm going to plug in 0 in for all the t's here. T cubed, that would be 0. There's a t there, so that term is 0. Sine of 0 is 0. Okay, I've got just C1 on that x component. Looks like if I plug in 0 into the y component, 2 times 0 is 0, so I'm left with C2 there. And then in the next one, I'm left with C3. This is going to equal that initial velocity of 0, 1, 2. So C1 is going to be 0. Let's see here. C1 is 0. C2 is 1. C3 is 2. All right, so that gives me all of those constants. I'm going to rewrite that velocity vector. All right, so now we've got the velocity at any time is t cubed over 3 minus t cosine t plus sine of t plus 0. Then 2t plus 1, because C2 is 1, and C3 is 2. All right, so there's my velocity. This question asks to find the position. We've got to do this all again. Take the integral of every single component. Okay. Here we go. Derivative of integral of t cubed over 3, so that would be t to the 4th over 12, minus, looks like I have another integration by parts or tabular. Notice how I just put the negative in front of the t. It distributes it for me, and then I don't have to think about it, because otherwise I'll forget to distribute that guy. All right, so the derivative down the first column, the second column, the integral of cosine is going to be sine. The integral of sine is negative cosine. Multiply diagonally, first one plus, next one minus. All right, so we've got a minus t sine of t. 1, 2, 3 negatives on the next term. Negative cosine of t. Okay, so that was the integral of t cosine. Now I've got the integral of sine. The integral of sine is cosine, and that one's going to be negative. I always have to think about those negatives. All right, integral of 2t, that'd be t squared. Oh, hang on, just forgot a constant. Back up. Plus a c1. Okay. Now, the integral of 2t is t squared. The integral of 1 is t, and I'll add another constant. And on that last term, the integral of 2 is 2t, and I will add a constant, c3. Okay, one more step here, hoping I can fit all of this on this page. The initial position was the origin. This is going to allow us to solve for the C1 and C2, C3 that we now have. This is a new C1, C2, and C3. Maybe I should have called them something different. Maybe we could just put a little star by them. There. Now there's something different than the other C1, C2, C3. Let's plug in 0. Okay, so the position at 0, t to the 4th over 12, that's going to be 0. We've got a t in this term, that's 0. Cosine of 0 is 1, so there's a minus 1. Here's another one. A cosine of 0 is 1, so another cosine, that's a minus 1 as well. Plus that c1 star. Plugging in 0 into this next term, we've got 0, 0, c2. And into the next one, 2t, well 2 times 0 is 0, we've got c3. And the initial position, we're told that the initial position is the origin. So this means that C2, I'm pulling off C2 first and C3 because those are pretty easy to see that those are 0. C1, on the other hand, -2 plus C1 is 0, so that means C1 is going to have to be 2. Now I can write down my position. Actually, I'm going to move this over a little bit because this is going to be a little long. All right, position at any time. For the x component, I have t to the 4th over 12 minus t sine of t. Now I have 2 cosines here. I'm going to combine those. I've got 2 of them, so that's minus 2 cosine of t plus c1. That's plus 2. Now I've got, for that second component, t squared plus t, c2 was 0. And for the third one, 2t, and c3 was 0. Whew. Okay, so this gave you a couple different, well, quite a few different things that we can do with vector valued functions. We can find domain, we can find limits, derivatives, integrals, we can compute velocity vectors, acceleration vectors, position vectors, going back and forth using derivatives and integrals in those.